Good afternoon, all of you. In yesterday's class of thermodynamics, we studied about what is a system, what is a surrounding, and what makes the boundary. And we also studied about three types of systems, which were isolated system, closed, and open system, which were divided or classified on the basis of exchange of matter and energy. I hope you all are clear with that. So now moving on to the next portion, which is the state of system. Yesterday we studied about what is system. So system is a part of universe where we carry out our studies in. So that is a system. It can be a liquid, it can be a gas or whatever. So system is a part of universe which we are carrying out our thermodynamic studies. And the state of system. Here the word state does not tell us about the state of matter or whether it is solid or liquid or something. It is telling about the conditions at which the system is existing. So the state of system tells us about the condition where the system is existing. For example, if we take a system, the initial condition and final condition is being represented by terms like pressure, temperature, volume, and number of moles in it. So if we want to tell about the state of a system at particular condition, then we need to tell this kind of terms of it. So a system at particular pressure, temperature, volume and number of moles will show us at what condition the system is existing, right? So if we tell all this, we can understand at what state the system is existing. So that is the state of system. And we have two types of functions or terms which we can represent a system, which are state functions and path functions. So we will see what a state function and path function is. So a man is planning to climb a hill and I am going to study about his potential energy. So potential energy of a body is PE is equal to mgh. The potential energy is equal to mgh is the equation. So m is the mass, g is the gravitational constant and h is the height. So when he is in the floor or when he is in the ground, the h term will be equal to 0. He is not gone to any height. So when he is in the floor, the height is 0. He is not transferred to any height. So when h becomes 0, potential energy will become 0. Then the person start climbing the hill in this way. So he just climbed like this to the upper portion. There the potential energy will have some value because the height is increased. There he is having a mass, he is having gravitational constant and he is also having the height. In this case height was 0, so the potential energy was also 0. In this case PE will have some value as the height is increased. And next time he came down and he is again climbing the hill through a different way, which is like this. So first way was a straight line like this, and in the second way he climbed like this. Through a long route he went up to the hill. In this case, if I calculate the potential energy, will that be any difference between the initial stage what I calculated? No, because here also the height is the same thing. Here the potential energy is just mattering on how much the height is changed. Whether he climbed like this or if he climbed like this, in both the cases he climbed up to same height. So height is the only factor which we are concerned about. So the distance or the path which he traveled is not a matter here. And now I am going to consider not the potential energy but the distance traveled by this man. If I consider the distance traveled by this man, then will it be the same thing in this case and in this case? No, because in the first case he traveled lesser distance than that of the second path. So there the path matters. So when we consider the potential energy, if he traveled through this path or if he traveled through this path, the quantity remains the same because it is just concerned about the height. But when I calculate the distance traveled by this man, then this path is having a lesser distance and this path is having more distance. So the type of functions where the path matters are known as path functions. For example, as we discussed here, distance. But the functions which the path is not a matter, they are known as state functions. In state functions, we are just concerned about the initial state and the final state. How he traveled here is not a matter in state functions. There, the final state and the initial state is the only consideration. This is a physics type of explanation. In chemistry, if we try to explain it, we can consider this reaction where A plus B gives C. If we are considering another reaction where we get A plus B gives K, which again gives C. In the first case, we have two reactants and a product. But in the second case, the reactants are first converted to an intermediate state and then it is converted to the real product. If we are considering the state function, then both the reactions are also same, as state function does not consider the intermediate state or how A plus B is converted to C. The method is not important in state function. We are just concerned about the initial state and final state. So as the initial state and final state is same in both the reactions, state function will tell these two reactions as same. But in case of path function, it is different because it considers the intermediate state also, or it considers the path where it followed. So this is the difference between state function and path functions. And in thermodynamics, we are concerned about the state function than that of path function. So the state of a thermodynamic system is described by its measurable or macroscopic properties. So this we have told in the first class. So thermodynamics mostly concerned about the macroscopic properties. We can describe the state of a gas or anything by quoting its pressure, volume, temperature, amount, etc. Variables like pressure, volume, temperature are called as state variables or state functions because their values depend only on the state of the system and not how it is reached. So their values depend only on the state of the system or just about the initial state and the final state and not on how it is reached. So such kind of variables are known as state variables. In order to define a system, a state of a system, it is not necessary to define all properties of system, as only a certain number of properties can be varied independently. So if we keep one of them or two of them constant, the other term is fixed. So such kind of reactions we have done in states of matter also. So we don't have to define everything properly because if we take one of them or two of them constant, we can identify the other terms. So we don't have to, or necessarily it is not needed to define all the properties of a system, as only a certain number of properties can be varied independently. So independent variation is difficult in state variables. Internal energy as a state function. In this topic, we will see what is internal energy and how internal energy is a state function. So what is internal energy? Internal energy, represented by the term U, is a quantity which represents the total energy of a system. So if we consider a system, internal energy means its total energy. It is the sum of its chemical energy, electrical energy, mechanical or whatever energy the system is having. Sum of all that is known as its internal energy. Internal energy of system can be changed when heat passes into or out of the system. Just think of a reaction, chemical reaction. A reactant we are taking and we are heating it. Once we heat it, the energy of the reactant increases, right? So when the energy increases, internal energy also increases. So heating is a method which we can increase the internal energy, and cooling is a method which we can decrease the internal energy. And work is done on the system or by the system. For example, we are taking a chemical in a beaker and we are mixing it with a spoon or spatula. Then what happens? When we mix it, the kinetic energy of that particular chemical increases, right? So we are moving the chemical inside the beaker. So hence the kinetic energy of that particular thing increases. Hence the internal energy also increases. So when work is done also, we can change the internal energy. And matter enters or leaves the system. So when matter changes, energy also changes. Hence, these are the three methods where we can change the internal energy of a particular system. Now we will see it one by one. So first we will be saying about the work, or how internal energy can be changed by applying work. So delta U with work, or change in internal energy with work. So for that we have an apparatus with a particular system. For example, we have taken water in it, and water we have taken inside a container, and we need to have an extra wall or a covering so that the energy of this particular system will not go out, or any other energy from the surrounding should not enter inside the wall. So this is somewhat like an isolation. The system will not allow its heat to go outside, or it will not allow the heat to enter from outside to inside the system. So this type of system is known as an adiabatic system, where it does not allow exchange of heat between the system and surroundings through its boundary, and we call this type of system as adiabatic. So adiabatic system is a kind of system which will not allow exchange of energy between the surroundings and the system. So adiabatic process is a process by which there is no transfer of heat between the system and surroundings. So the wall separating the system and the surrounding, and the insulation type of wall is known as the adiabatic wall. An adiabatic system will look like this. So this wall which separates the surrounding and system is known as the adiabatic wall. So there is no exchange or supply of heat. So Q will be equal to 0, or the change in heat is equal to 0, and the matter and energy will be inside the container only. So here we are going to study about the change in internal energy of the system in an adiabatic container with the use of work. So we are going to do some work inside the container, and we are going to observe the changes of internal energy. So for that we need the initial stage to be A. So A is the initial stage of this container and the system. So at the stage A, temperature of the system is TA and the internal energy of the system is UA. And now what we are going to do is, we are going to do some work inside the container. So let's consider the system to be water only. So in the water we are adding a pedal which we can operate from outside. So this pedal is going to do some amount of work, or 1 kilojoule of work inside the system. So when the pedal is going to rotate, it is inducing some amount of work inside the system. So we are going to start the pedal. So pedal started working. So when it is working, the kinetic energy of this system is increasing. So when the pedal is rotating, the kinetic energy of this system increases. So as the kinetic energy increases, the temperature also increases. So initially the temperature was TA and the internal energy was UA. But after the pedal rotates, the final state will be TB and UB, which will be more than that of the final state. So when it rotates, temperature increases and the internal energy is also increased. So we can tell TB is greater than that of TA as the temperature increased, and UB is greater than that of UA. So as the kinetic energy increased, the internal energy is also increased. So this is what we got from the work done on the system. So the change in temperature is TB minus TA, or the change in temperature from the state A to state B is TB minus TA, and the change in internal energy or the delta U is equal to UB minus UA. So these are the observations after we done a mechanical work inside the system. Now we are going to do some other work. We are going to induce electrical energy inside this. So we have dipped a rod inside this and we are inducing electrical energy to the system. So there also the initial temperature is TA and the initial internal energy was UA. So as we induce electrical current to the system, there also the temperature and internal energy increases, and it increases to TB and UB. Here also, as increase in the temperature and internal energy occurs, we can tell the delta T is equal to TB minus TA and delta U is equal to UB minus UA. So now we are comparing the both cases. In the first case, we induced mechanical energy to the system, and in the second case, we induced electrical energy to the system. But in both cases, we gave 1 kilojoule of work. With the mechanical energy and with the electrical energy, we gave 1 kilojoule work to the system, and hence the changes was same. So in the mechanical energy, initial temperature was T1, and after the mechanical energy, the temperature T2 was shown, and the internal energy changed from U1 to U2. So this is the case of first experiment. And in the second experiment, when we gave electrical current, the same changes was observed. The temperature was changed to T2 and internal energy from U1 it changed to U2. So in both the cases also, the change in temperature and internal energy remained the same thing, or the delta U and delta T was same. So with this we can tell that delta U or the internal energy is a state function because it does not depend on the path. If we increase the U1 to U2 by mechanical energy, and if we do the same thing with electrical energy, we got same results. So in the first case also it changed from U1 to U2, in the second case also it changed from U1 to U2. The change is same. So we can tell it does not depend on the method which we used, or it does not depend on the path which we used. So hence when it is independent of the path, we can tell the delta U is a state function, not a path function. So that's what we were doing. So we proved that delta U or change in internal energy is a state function. The internal energy U, whose value is characteristic of the state of a system, where the adiabatic work. So the adiabatic work means the work done on an adiabatic system without exchange of energy with the surrounding. So that is adiabatic work. So this adiabatic work required to bring about the change of the state is equal to the difference between the value of U in one state and that of the other state. That will be clear by the equation. So the delta U is equal to U2 minus U1. This equation we have seen. which is equal to the work done on the adiabatic system. This is what we explained here. So the change in internal energy is equal to the adiabatic work which we have done. There is no change for the work which we have done from the internal energy change. Therefore, we can tell internal energy of a system is a state function. It does not depend upon the path which we used. It is independent of the path. So, we can tell internal energy is a state function. So, one more factor is we are comparing work is done on the system and work is done by the system. So what we have done here is when work is done on the system, we are doing work on the system because we kept the piston or we kept the pedal, we rotated that and we done work on the system. So what happened there? Initially the internal energy was U, and when the work was done on the system, the internal energy of the system increased. So the change in internal energy is from U1 to U2. Initially it was a lesser quantity, then we did work on the system and hence the kinetic energy increased and hence the internal energy also increased. So U1 is a lesser quantity and U2 is a bigger quantity. So when we substitute that in the equation, when U2 becomes a bigger quantity, we will get WAD as a positive value, or work done on the adiabatic system will become a positive value. But when the work is done by the system, it's a different thing. So here we are just adding the piston, just consider like that. So system is doing some work. Initially the internal energy is U and the system is doing some work, and that work is inducing the mechanical energy to happen. So see that again, the system is doing some work and because of that work the piston or the pedal is rotating. Initially we rotated the pedal and system worked. Here the system is only working and because of that work the pedal is rotating. So when the system is working itself, the internal energy of the system will decrease. So when the system is working, the working person's energy will decrease, right? For example, if we go out and work in a field, our energy will decrease, right? Because we are working. So similarly, the system is only working here so that the piston is rotating. So hence, the internal energy of the system will decrease as it works. So internal energy of system is decreasing when work is done by the system. So the energy change will be U1 to U2. Initially the energy was more and after working the internal energy decreased. So when U2 is a lesser quantity than that of U1, what is the change occurring here? So U1 is a bigger quantity than that of U2. Hence we will get a negative value of work. So when work is done by the system, WAD will be a negative value as the U1 is a more bigger quantity than that of U2. So concluding, when the work is done on the system, then the internal energy increases, hence WAD, the work adiabatic, is a positive value. And when the work is done by the system, then the WAD is negative as the internal energy decreases. So with that we wind up our session. So we discussed a lot of concepts today. So please go through the video once again and be clear with these concepts. And please ask if you have any doubts in these concepts and prepare notes by help of your textbook and submit in the group. Thank you.